In lecture 7, we're going to be talking about something called stereochemistry. This is chapter 5 in Wade, and the focus of it is something we call asymmetric carbons, and it involves thinking in 3 dimensions. You might recall in the first lecture we did, I mentioned that the 3D structure of organic molecules is really important to determining their behavior in some very specific contexts. And stereochemistry kind of gets at the heart of that. So to review, in previous chapters, we talked about isomers, and we looked at a couple different types of isomers. Remember that isomers are molecules that have the same formula, but a different structure. And we looked at 2 types of isomers that were constitutional isomers, where the atoms are literally connected in a different sequence. They have different bonding. So for example, this structure here is 5 carbons with a nitrogen and a certain number of H's. This is also 5 carbons, a nitrogen, and the same number of H's. You can see they have the same formula, but clearly different structure, different connectivity. Same thing here. We have the same formula, same number of carbons, same number of hydrogens, but different connectivity. This carbon here has 3 hydrogens on it. This carbon here has 2 hydrogens on it, etc. Those are constitutional isomers. They are constitutionally different. They are fundamentally different. But then we looked at a second type of isomers that we called geometric isomers that had the same connectivity in addition to having the same formula. The atoms were connected in the same sequence, but they had a different geometry across the double bonds. So you'll notice that in this pair of molecules, we've got a CH3, then a CH, double bonded to a CH, bonded to a CH3. Here we also have a CH3, bonded to a CH, double bonded to a CH, bonded to a CH3. So the same sequence, the same connectivity, but the difference between these is that the geometry of the double bond is different. We said that this was a trans double bond because the H's were on the opposite side, and this was a cis double bond because the H's were on the same side. You'll recall that because you cannot rotate around a pi bond, that means that you can't interconvert cis and trans simply by rotating that bond. These atoms are kind of stuck in this spatial arrangement, and these atoms are stuck in this spatial arrangement, and you can't interconvert them unless you break the double bond and then reform it in the different geometry. So there's no interconversion between these 2 things, and as such, they have unique properties. I also mentioned that this is another type of pair called stereoisomers. Geometric isomers are a type of stereoisomers that they always come in pairs. So I want to make a slight clarification. That is that trans and cis, that nomenclature that we use, really actually in reality describes the relationship between 2 groups. It doesn't really describe the geometry of the double bond. For example, we could say that these 2 hydrogens are trans to each other, and these 2 methyl groups are trans to each other. And we could say that these 2 hydrogens are cis to each other, and that these 2 methyl groups are cis to each other. But since cis and trans refer to a relationship, we could also describe this methyl group as being trans to this hydrogen. They are on the opposite sides of the double bond. Same thing here. We could describe this methyl group and this hydrogen as being cis to each other because they are on the same side of the double bond. So cis and trans is, remember, a relationship. It describes the relative positioning of 2 groups. So for something like this molecule, which is called 2-butene, we'll talk about naming alkenes in a little bit, but this is called 2-butene, this is trans 2-butene, and this is cis 2-butene. The cis and the trans actually is sufficient for a simple system like this. But if we were to look at this pair of molecules here, I guess that you would say that it doesn't really make sense to call one cis and one trans. If I were to look at this, is this cis or is it trans? Or this, is it cis or is trans? Because the question then becomes that once you realize that cis and trans refers to a relationship, two positions relative to each other, the question is then, what is the relationship that we're looking at? This is more complicated. We need a more sophisticated way to reference this molecule from this molecule. We can't say that one is cis and one is trans because we don't have any two similar groups that we could say are cis or trans to one another. So let's look at a more sophisticated system of nomenclature for when we have double bond geometries with more complicated groups around them. Instead of using cis and trans, what we really should use when we're talking about geometric isomers or the geometry around a double bond are E and Z. These refer to the German nomenclature. E refers to the German word entgegen, which means separate, and Z stands for refers to the German word zusammen, which means together. So I want to show you how we can discern one molecule from the other by using a different system that we're going to call E and Z. What we're going to do is we're going to order the atoms on each double bonded carbon by what I'm going to call stereochemical priority. In a lot of ways, chemical priority is just size or molecular weight, but it's actually more than that. So don't get locked in yet to the idea of stereochemical priority meaning size, but follow along, see what I mean by this. So what we're going to do is we're going to look at each carbon that is involved in the double bond. So we said we're going to order each atom or order atoms on each double bonded carbon by priority. So here are the two carbons that are involved in the double bond. Let's look at the atoms on the left carbon and let's rank these guys by priority, which basically means molecular weight. So if we're going to rank chlorine versus fluorine by molecular weight, chlorine would be first. It's the highest in molecular weight. Fluorine would be second. So we'll say chlorine is 1, fluorine is 2. We do the same thing for the other carbon. The atoms on this carbon are bromine and iodine. So ranking those based on molecular weight, I would take priority over Br. So we have chlorine and iodine are 1s, fluorine and bromine are 2s. And if we look at the similar groups, so the 1s or the 2s, and we draw a line right through the double bond like this. If the similar groups, say the 1s are on the same side, then we call it Z. I like to say Z stands for the same side. If these groups are on the same side, this is a Z double bond. So we have the 1s on the same side and 2 on the same side. So that's the Z geometry. That's the Z. Let's do the same thing with the other molecule. We will, again, identify the carbons that are involved in the double bond, and we're going to rank each atom attached to those carbons as a 1 or a 2. So again, on the left carbon, we've got chlorine and fluorine, and again, chlorine is 1, fluorine is 2. On the right atom, again, we've got bromine and iodine. Iodine is 1, bromine is 2. So we will rank those like that. We will identify the same groups. So those are the 1s. We could also identify the 2s. We draw a line right through the double bond like that. And since the 1s are on the opposite side, they are not on the same side, they are on opposite sides, that is the E geometry. So we've got 1Z, where the larger groups are on the same side and the smaller groups are on the same side. And we've got E, where the larger groups are on the opposite sides of each other. So this is similar again to the idea of cis and trans, but it lets us group things not based on whether they are both methyl groups or whether they are both hydrogens like we did before, but group them based on their, what I'm going to call stereochemical priority, which is based on molecular weight. So we could say, in this case, that the chlorine and the bromine, those are trans to each other because they are on the opposite side of the double bond. So we could say those are trans, but the whole double bond, when taken as a whole, when looking at everything that's attached to it, including the fluorine and the iodine, of course, the whole double bond is Z. Fluorine and bromine are cis to one another. Chlorine and iodine are cis to one another. Chlorine and bromine are trans to one another. Iodine and fluorine are trans to one another. Those relationships are true. We have some cis relationships and some trans relationships, but the overall double bond is a Z double bond. Okay, let's keep going. We're going to do a slightly more complicated example. Let's figure this one out. We'll look at this double bond right here. This double bond you couldn't classify as E or Z because the oxygen doesn't have anything attached to it. So we'll look at this carbon-carbon double bond right here. So again, identify the double bond. We're going to identify the two carbons that are involved in it. And then we're going to look at what are attached to those carbons. So let's start with the carbon on the left. Now here's where it gets tricky. Let's look at what that carbon is attached to, or what groups are on this carbon. Well, we've got two carbons, right? We've got a carbon here, and we've got a carbon here. Those are both carbons. So that's a tie. We can't say that one carbon is higher in priority than the other carbon. So in the event of a tie, we have to look at what these carbons are subsequently attached to. This carbon down here only has 3 hydrogens on it. It's a methyl group. This carbon here has 2 other methyl groups on it. So if we were going to rank this by stereochemical priority, which is again basically molecular weight, we would give this carbon higher priority because it has more high priority groups attached to it than this guy does. So we would rank the isopropyl group as being 1, the methyl group as being 2. Let's look at the other carbon. The same way that the first carbon had 2 carbons attached to it, this carbon also has 2 carbons attached to it. We have this carbon and this carbon. So again, when you have a tie where the 2 atoms connected have the same molecular weight or the same atomic weight, we're going to look at what those carbons are attached to. Now, this carbon down here has another carbon on it. It's got a methyl group on it. It's got 2 hydrogens and a carbon. This carbon has the double bonded O and a hydrogen. Now, for the purposes of stereochemical priority, the double bonded O counts as 2 oxygens. Imagine that this carbon has 2 bonds to oxygen. Whether it's the same oxygen or different oxygens does not matter. But based on stereochemical priority then, this group up here would have a higher priority because this carbon has 2 oxygens and a hydrogen. This guy has 2 hydrogens and a carbon. So much more molecular weight on top in this aldehyde group than on this ethyl group down here. So this will be stereochemical priority 1. This will be stereochemical priority 2. We draw the line right down the middle. Notice that the similar groups, the 1s are on the same side of the line, and the 2s are on the same side of the line. and that is a Z double bond. The geometry of that is Z. Now, I want to show you why stereochemical priority is not molecular weight. It's related to it, and in a lot of times, in a lot of examples, in a lot of contexts, stereochemical priority will follow molecular weight perfectly, but it's not the same. Watch what we do. So let's identify our double bond. So here's our double bond, and we're going to look at the groups that are attached to these carbons. So notice that we have a very, very, very large chain of carbons up here. But remember, I'm going to prove to you that molecular weight does not refer to specifically stereochemical priority. Let's do the groups on the left here first. So this is easy. We've got our carbon here. That carbon has two groups on it. It's got a hydrogen and a methyl group, a CH3. So carbon is higher priority than hydrogen. So that's going to be our 1, hydrogen is going to be our 2. On the right side, our carbon on the right, we have two carbons attached. We have this carbon and this carbon. So again, when the two atoms attached have equal priority, we look at what those atoms are attached to. What is attached to this carbon? Well, he's got two hydrogens and another carbon. This carbon, however, has 3 carbons. So this guy down here, this carbon on the bottom, gets higher priority. He has more high atomic weight atoms attached to it than this guy does. So once we've broken the tie, once we've done our tiebreaker and said, what are these atoms subsequently attached to, and we come to a difference in priority, we're done. We can stop there. So this group gets higher priority than this group, even though this group might continue on for 100 or 200 or 300 carbons. What comes after our tiebreaker doesn't matter. So there we go. We can draw a line right through the double bond, identify that the similar groups, the 1s, are in this case on the opposite side of that line, and the 2s are on the opposite side of that line. So this is an E double bond. We can do more practice in the workshop. Let's move on to another aspect of stereochemistry. This is a term that might not be familiar to you. It's called chirality. The term chirality refers to any object that has a left-handed form and a right-handed form. Any object that has two forms like that is said to be chiral, or to have the property of chirality. What you want to do to determine if an object is chiral is look at its mirror image. If the mirror image of the object is the same as the object itself, then the object is not chiral. We say it would be achiral. If, on the other hand, the mirror image is different from the object itself, then the object is chiral. You can see here that the chair, when reflected in the mirror, you could take this chair in the mirror and imagine sliding it back over the original object, and everything would line up perfectly. That is to say that the mirror image is exactly the same. It is superimposable on the original object. That is achiral. That chair is achiral. On the other hand, like we said, if you have a right hand and you reflect it in a mirror, the mirror image is not superimposable on the original object. If you take this left hand and slide it over the right hand, obviously they're not going to line up. The thumbs will not line up and the pinkies will not line up. The object in the mirror is different than the original object, or the image in the mirror is different than the original object. That means that your right hand is chiral. Of course, that makes sense. You have a right-handed hand and a left-handed hand. Your hands are chiral. They have the property of chirality. Let's look at some other objects. This is kind of fun. This is an MG. It's a British model car, and you can see that the steering wheel is on the wrong side. The steering wheel's on the right side of the car. So it's a British car, and they had some fun with this because they reflected this object in a mirror, and they played a little trick. They turned MG into GM, which is an American car, and now the steering wheel is on the left. So you can see that our original image had the steering wheel on the right. Our mirror image had the steering wheel on the left. These are not the same objects. If you take the mirror image and you try to rotate it back over, slide it back over, and line up the mirror on the original image, the steering wheels are going to be on the wrong side. So this is a chiral object. Here we've got a screw, and you see that the threads are going a certain direction. They're slanted in a certain direction. If you take the mirror image, you reflect that object in a mirror, you now have the threads going in the other direction. And if you take the reflected object, if you take the mirror image, it is non-superimposable on the original. If we tried to take this image, this mirror of the screw, and slide it over on top of the original object, they're not going to line up. The threads are not going to line up. So this is a chiral object. You have left-handed screws and right-handed screws. Here's scissors. So this is a little bit more tricky to see, but we've got a smaller loop, which is on the bottom, and a larger loop, which is on the top. And if we flip that in a mirror, we reflect it in a mirror, still we have the large loop on the top and the small loop on the bottom. But if you try to slide it back over the original image, it doesn't line up. If we try to just slide this over, we're going to have the large loop here. This loop will slide up here, and the small loop will end up down here. So if we just slide it over, our loops don't line up. If instead we flip this object over, we can get the loops to line up, but if we flip this over, the small loop will be on the top, and here the small loop is on the bottom. So the mirror image is non-superimposable on the original object. I'm using that term a lot, non-superimposable, because chiral objects are non-superimposable mirror images of each other. Now, it turns out that molecules can be chiral as well. Why would we be talking about chirality if it didn't apply to chemistry? Let me point out something before we move on, actually. I want to show you that an achiral object, like this chair, is achiral because itself has a central mirror plane. This chair itself is a symmetrical object. You can draw a line right down the center of this chair, and one side of that line will be the same as everything on the other side of that line. If the object itself is symmetrical, then its mirror image will be superimposable on the original object. But if the object does not have an internal mirror plane, you can't draw a line through your right hand that cuts it in half exactly, then your object will be chiral. The mirror image will be non-superimposable. So applying that to molecules, we have two different molecules here with different stereochemistry. Notice that I'm using this dash and wedge notation. Remember that dashes refer to the group going backwards, kind of into the plane of the board or into the screen. And the wedge means that the group is coming out of the screen, out of the plane of the board. So these are different. These molecules are not the same. They have the same connectivity. They actually have the same formula. Of course, they're isomers. They have the same formula. They also have the same connectivity. But there's something else that's different about them. Even though there's no double bond, the orientation of the groups in space is different. These two chlorines are both underneath the ring. If you imagine this ring sitting flat in the plane of the board or in the plane of the screen, these chlorines are both going into the screen. Here, one chlorine is coming out and one chlorine is going in. So these have very different three-dimensional structures. even though they are constitutionally the same. They have the same connectivity. So this structure on the right, notice that there is an internal mirror plane. You can draw that line right down the middle, and everything on the left side is the same as everything on the right side. So that's a clue that this molecule will be achiral. This is not going to have a left-handed form and a right-handed form. Another way to look at this would be kind of in perspective. If you're kind of looking at this ring from the side, kind of from this end, you would see 2 chlorines going down and 2 hydrogens going up. And notice that because of the symmetry of this molecule, there's that mirror plane down the middle. If you reflect this molecule in a mirror, and here's the reflection of it, notice that this molecule is the same. The reflection, the reflected image, is the same. It can be slid, you can slide it right over on top of the original image, and all the carbons will line up, and the hydrogens will line up, and the chlorines will line up. They're using cis here, even though there's no double bond, because these chlorines are kind of on the same plane of the ring. They are both sitting underneath the plane of the ring, and the hydrogens are sitting above the plane of the ring. So sometimes this will be used to reference a 3-dimensional picture and not just the geometry around a double bond. So these are the same. The mirror image is superimposable on the original, so it's the same. It's an achiral molecule. But look what happens here. When we don't have that internal mirror plane, we can't draw a line right down the middle of this molecule because the left side will have a chlorine up and the right side will have a chlorine down. To look at this molecule in perspective, you'd have this chlorine up above the plane of the ring, this one right here, and this chlorine down below the plane of the ring. And the hydrogens, this hydrogen is dashed right there. It's not drawn, but it would be dashed. This hydrogen right here would be wedged, so it would be up. So that hydrogen is up, this first hydrogen is down. If we reflect this in a mirror, notice that we get a different molecule. This carbon right here reflects to this carbon right here. This carbon right here reflects to this carbon right here. Now, if we take the mirror image and we slide it over, the carbons will still line up, that's fine, but the hydrogens and the chlorine will not. This hydrogen would slide over and it would sit on top of that chlorine, and this chlorine would slide over and sit on top of that hydrogen. So we have a molecule that has an asymmetrical geometry. It does not have an internal mirror plane, and so the mirror image of it is non-superimposable. So this is a chiral molecule. These two are different things, so this molecule is chiral. Non-superimposable mirror images. So I want to point out what's going on here. What is causing the molecule to be chiral? Now, obviously, I mentioned that an internal mirror plane will cause a molecule to not be chiral, and no internal mirror plane will cause the molecule to be chiral. But where is that coming from? If we look closer, here's another model. This is 2-bromobutane. Here's butane. It's 1, 2, 3, 4 carbon chain. It's got a bromine on the second carbon. This is the drawing here. They kind of drew this in the line structure to kind of represent the 3-dimensional structure. You see that this bromine is coming out forward towards us. This hydrogen is tucked behind the molecule. So that hydrogen would be drawn as a dash. This bromine would be drawn as a wedge. If we flip this molecule around, or not flip it, but if we take a reflection in a mirror and we kind of reflect everything across this mirror plane, this bromine reflects here, this carbon reflects here, that hydrogen reflects there, the methyl group reflects there, this carbon reflects there, this carbon reflects there. These molecules are now different. First of all, if you take this molecule, the mirror, and you just slide it over, nothing lines up. This methyl group would end up over here. The bromine would end up over here. nothing would line up. If we just took this guy and slid it over, nothing would line up. If we rotated this guy 180 degrees, kind of flipped it around, it also still would not line up. The carbons might line up. If we flip this around, all the carbons would line up, but the bromine would be pointed backwards. Notice that the bromine is forward here, the bromine is forward here, but if we flip this guy 180 degrees, this bromine would be pointed backwards and it would not line up. Where is that coming from? It's this carbon right here. The carbon with this little asterisk on it has 4 unique groups. And by unique, I mean 4 dissimilar groups. What are those 4 dissimilar groups? There's a methyl group, a CH3. There's a hydrogen. There's a bromine. And you can see this group as an ethyl group. It's a 2-carbon group, an ethyl substituent. This carbon also has a methyl, an ethyl, a hydrogen, and a bromine. 4 dissimilar groups. The way they are connected to that carbon is different. I have a 3D model here. This is the molecule we were just looking at, and I have it positioned the way it was positioned in the book. You can see that we have our 4 carbons, 1, 2, 3, 4. Here's the bromine, it's coming out towards us. You can see the hydrogen tucked around behind it. And you can see that this molecule has a very specific 3-dimensional shape. If we have the molecule arranged like this, like we had it in the book, the bromine is coming out towards us. If we flip it around, looking at it from the other side, the bromine's going away from us. So it's the same molecule, obviously, just depending on what side you're looking at it. That's not changing. But here's the first molecule with the bromine coming towards us. Here's the second molecule. This is the mirror image. The bromine is still coming towards us. But if we flip the molecule around so that it lines up, we try to line it up the way the first one was, like that, the bromine's going away from us now. So it's a different molecule. That guy, with the molecule, the bromine was going away from us. Here the bromine's coming towards us. So 1, 2, bromine away from us. The difference, the one thing that causes these molecules to be different from one another is the way that the 4 groups are attached to this one special carbon. I'm going to call that an asymmetrical carbon, a carbon that has 4 dissimilar groups attached to it. Sometimes that's called a chirality center. It is the focal point, if you will, of the chirality of the molecule. It is that carbon, the arrangement of the groups on that carbon, that gives rise to the asymmetry in the molecule. Let me prove to you why you need 4 different groups, why you need 4 dissimilar groups. A carbon's often going to have 4 different groups. You say one methyl is different from another methyl, for example. But I want to say dissimilar. I want to be very specific in that. So let's look at a carbon right here with 4 dissimilar groups. We're just going to call them group 1, group 2, group 3, and group 4. One trick that we can do is we can look at these groups and how they are positioned relative to one another. What we're going to do is we're going to look at these groups and look at how they go clockwise or counterclockwise from group 1 to group 2 to group 3 to group 4. We are going counterclockwise. Look what happens when we reflect this molecule in a mirror. Here's the mirror image, right? The 4 is reflected to the 4, the 3 is reflected to the 3, the 2 is reflected to the 2, the 1 is reflected to the 1. Look what happens. Now 1 to 2 to 3 to 4 is going clockwise. These are different molecules. We get a new molecule with the groups arranged in the opposite arrangement, in the opposite order, when we reflect our molecule in a mirror. You need 4 groups for that to be true. If you only have 3 groups, three dissimilar groups, look what happens. We've got group 1, group 2, and 2 identical group 3. So only 3 dissimilar groups. Here we're going to take our molecule and we're going to reflect it in a mirror. So group 1 reflects to group 1, group 2 reflects to group 2, and the group 3s reflect to each other. If we take that reflected molecule and we just rotate it 180 degrees, so group 2 switches around to here, groups 3 flip around over here, group 1 stays on top, we can take our, what is the mirror image, and we can slide it right back over the original. This guy is exactly the same as our original object was. So the mirror image is superimposable on the original one. And that will always be true if you have something fewer than 4 dissimilar groups. You cannot have chirality without 4 dissimilar groups. There are some exceptions. There are some really weird exceptions. I'll show you that in workshop, some of the weird exceptions where you can actually get a chiral molecule with fewer than 4 dissimilar groups, but they are very, very specific cases and they're very tricky. So for the most part, let's just think about it this way. 4 different groups, 4 dissimilar groups will make a carbon asymmetric. We can differentiate these guys by name as well, the same way that we could differentiate one double bond from the other, one being the E geometry, the other being the Z geometry. We can differentiate these carbons as having a certain orientation. How are its 4 groups oriented? Here's what you want to do. You want to view the molecule with its 4 dissimilar groups, with the 4th and smallest group, that is to say, the lowest stereochemical priority group, going towards the back, going backwards. So if we've got our molecule here, we want to view it with group 4, the smallest, lowest priority group, going backwards. Once you've done that, you are viewing your molecule with your smallest priority group in the back. You now have very clear view of the highest 3 priority groups. So group 1, group 2, group 3. Once you've oriented group 4 to the back, then you look at the remaining 3 groups and you see whether they are going clockwise or counterclockwise. So now group 1 to group 2 to group 3 is going clockwise, and we call that R. This is the R configuration. Here's the mirror image, right? You can kind of see that this molecule is the mirror image of this guy. We are going to view this from the perspective that puts the smallest priority atom or group towards the back. So 4 is towards the back. So just going to rotate this around this way and put 4th back. Now, when you look at group 1 to group 2 to group 3, they're going counterclockwise. So that is called the S configuration. These are called enantiomers of each other. This is the R enantiomer. This is the S enantiomer. We're going to talk about the term enantiomer a little bit later in greater detail. But for now, remember that R has the 3 biggest groups oriented clockwise, and S has the 3 biggest groups, highest priority groups, orientated counterclockwise. Where do these terms come from? R stands for right-handed. So this is going starting from 12 o'clock. This is going to the right. So this is the right-handed version. S, you say, well, why don't we use L or something for left-handed? S actually stands for sinister or sinistre, which is the Latin root for left-handed. The term sinister, evil, it used to be believed that people who were left-handed were evil or sinister in some way. So sinistre means really left-handed, not evil, but that's the root of it. So we have a right-handed version of a molecule and a sinistre left-handed version of the molecule. So we've been spending a lot of time looking at these nice, pretty three-dimensional model images of molecules. So let's practice doing this using some line angle notation. So here's a chiral molecule. If you were to name this, it would be 2-chlorobutane. It's a 4-carbon chain, 1, 2, 3, 4, with a chlorine on the second carbon. Let's identify the asymmetric carbon, the chirality center. It should be a carbon that has 4 dissimilar groups attached to it. It shouldn't be hard to identify. It's carbon number 2. What are the 4 groups attached to carbon number 2? Well, there's a chlorine, there's a methyl group, there's an ethyl group, a 2-carbon group, and let's not forget, there's a hydrogen on that carbon. In line angle, remember that you don't draw hydrogens. So it is a hydrogen there, we just haven't drawn it. I have now drawn it in for clarity's sake. Also, pay attention to the geometry of this. Since the chlorine is a wedge and the other 2 carbons are drawn in the plane of the screen, that means that we need one group that's going into the screen, and so that must be the hydrogen. So those are our groups. Let's rank them based on stereochemical priority. I've got them drawn in already, but let me prove to you why these are the rankings that they are. The 4 atoms that are attached to this carbon with 4 dissimilar groups are a chlorine, a carbon, another carbon, and a hydrogen. So clearly the highest priority, the highest atomic weight is the chlorine. So he's going to be 1. And the smallest, lowest priority is going to be the hydrogen. So he's going to be number 4. But for groups 2 and 3, they were both carbons. That's a carbon, that's a carbon. So whenever you have a tie, you need to look at what those atoms are attached to. This carbon on the left is a methyl group, so he only has 3 hydrogens on it. This carbon on the right, he's an ethyl group, so he has 2 hydrogens and another carbon. So he gets the higher priority. So we have chlorine with 1, the ethyl carbon is 2, the methyl carbon is 3, and the hydrogen is 4. This molecule has already been drawn with the lowest priority group going away from us. That hydrogen is already going back. So since that hydrogen is already going back, we can now look at the first 3 priority groups and figure out whether they're going clockwise or counterclockwise. So chlorine is 1, ethyl is 2, methyl is 3. We are going clockwise, so that is R. We would call that R2-chlorobutane. It's not just 2-chlorobutane. We actually can be a little bit more specific. It is specifically 2-chlorobutane with the 4 groups on carbon 2 arranged in this orientation in space, this configuration in space. Let's do a couple more examples. This is a molecule with 2 asymmetric carbons now. And what we're going to do is we're going to go through and we're going to assign R and S nomenclature to both of the carbons independently of one another. Let's first identify which carbons have 4 dissimilar groups. See if you can do it here a minute. Here they are. Let's find the 4 dissimilar groups. This carbon has a methyl group, has the nitrogen, it has the ring carbon, the carbon that has the rest of the ring on it, and there's also a hydrogen there. Remember, there's got to be 4 bonds. So if we've drawn 3, there must be a 4th, that's a hydrogen. Same thing over here. We've got a methyl group. We've got the hydrogen. It's not drawn, but he's there. We've got this ring carbon and this ring carbon. And hopefully you can see why they're different. This ring carbon has a methyl group on it and is also attached to a nitrogen. This ring carbon only has 2 hydrogens that are attached to another and is attached to another carbon. So both of these groups have 4 dissimilar groups attached to them, so each one should get its own R or S designation. Let's start with this one. I'm going to do us a favor and draw in the hydrogen. Again, since we already have 1 dashed group and 2 groups that are in the plane of the board that are lines, we need 1 group that is coming out at us, so it must be the hydrogen. Let's assign priority to these groups. See if you can do it. What would be the highest priority atom attached to this carbon? Well, it would be the nitrogen. Nitrogen is going to be 1. What about hydrogen? You can guess hydrogen is going to be last. So nitrogen would be the highest priority. Hydrogen would be the last priority. The other 2 groups are the methyl carbon and the ring carbon. So between these 2 carbons, it's a tie. So we have to look at what those carbons are attached to. This carbon has 3 hydrogens on it. This carbon has this methyl carbon and the rest of the ring. So this group would get a higher priority. This carbon would get a higher priority than this carbon would. So we have nitrogen 1, ring carbon 2, methyl carbon 3, hydrogen 4. Now, here's the trick. Notice that we're looking at this molecule from the wrong side. We should be looking at this molecule with the hydrogen going backwards. Remember that in order to assign stereochemical priority, the 4th group needs to be going backwards. So here's a trick. Rather than worrying about flipping the molecule over or redrawing it or trying to visualize it from the other side, if the 4th group is not back, but is forward like it is here, then clockwise or to the right would be S, or left counterclockwise would be R. Imagine that you're just looking at this molecule from the wrong side. If you look at a clock from the correct side, it goes clockwise from 12 to 1 to 2 to 3 to 4, etc. If you look at that same clock, but from the back side of the clock, you would see from 12 to 1 to 2 to 3 to 4 going counterclockwise. It's the same idea. The molecule designation, the R or S designation, should not change depending on what side of the molecule you're looking at it from. You just need to have a designation that says what direction the groups are going relative to one another. And since it changes depending on what side of the molecule you're looking at, you just need to correct for that if you're looking at it from the wrong side. So if the H is coming forward, or if your smallest group is going forward, then your definitions go backwards. Your definitions flip. So since group 4 is going forward, we look at group 1 to group 2 to group 3. That's going counterclockwise. So normally it would be S, but we're looking at this molecule from the wrong side. So these groups are not truly counterclockwise. They are actually clockwise. If we were to look at this molecule from the other side, 1 to 2 to 3 would look like it's going clockwise. So this is R. That stereocenter, that's a term I'm introducing here, that stereocenter, that chirality center, is the R configuration. Let's look at this guy now. Here's our hydrogen. Again, we've got 1 dashed group, 2 groups that are in the plane of the board. So we need one group that's coming out at us. That's going to be the hydrogen. Let's rank these groups. This is a little bit more tricky because we've got 3 carbons now. We can clearly see that the 4 groups are a carbon, a carbon, and a carbon, and a hydrogen. So hydrogen is going to be last. What we need to do is we need to prioritize these carbons. Let's look at what these carbons are attached to. Since they're all carbons, we need to break the tie. This carbon is a methyl carbon, so he just has 3 hydrogens on it. This carbon, the ring carbon, has 2 hydrogens and another carbon. This carbon has a carbon, a hydrogen, and a nitrogen. So we've got 3 hydrogens, we've got 2 hydrogens and a carbon, or we've got 1 hydrogen, a carbon, and a nitrogen. So clearly this carbon is going to be the highest priority because he's got the nitrogen on it. This carbon is going to be next since he's only got a single carbon. And this guy is going to be last because he's got 3 hydrogens. So here's our priority. And again, we are looking at this molecule from the wrong side. The H is coming towards us, not going away from us. So we can look at groups 1, 2, and 3. 1, 2, 3. We see that it's going counterclockwise. So it normally would be S, but since the group is the 4th group is coming towards us, it's actually R. So both of these stereocenters, both of these chirality centers are in the R configuration. And we would name the molecule accordingly. You see how it's done here. The name of this molecule is pyrrolidine. It's actually a dimethylpyrrolidine. Don't worry about this for now. But the numbering starts on the nitrogen. So nitrogen is 1, this would be 2, this would be 3, this would be 4, this would be 5. So based on that numbering system, we have methyls on the 2 carbon and the 3 carbon. So this is 2,3-dimethylpyrrolidine. And the and the 2 is in the R configuration, and the 3 is in the R configuration. So we would call this 2R, 3R, 2,3-dimethylpyrrolidine. Now I want to go back to talking about relationships. Remember that we determined that this molecule, this 2-chlorobutane, where the chlorine was wedged like this, was R. We went through and we said chlorine was 1, the ethyl carbon was 2, the methyl carbon was 3. They're going clockwise, the H is going backwards, and so it's R. If we were to change the geometry, change the configuration of this chiral carbon, make the chlorine a dash and the hydrogen a wedge, for example, we would get S. Again, we could number these in terms of priority. The priority doesn't change. Chlorine would still be 1, the ethyl carbon would still be 2, the methyl carbon would still be 3. We are going clockwise in both cases. Clockwise from chlorine to ethyl to methyl, that's clockwise. Chlorine to ethyl to methyl, that's clockwise. But in this guy, we're going clockwise with the hydrogen coming towards us. This guy, we're going clockwise with the H going away from us. So these are opposite designations since, again, the H is coming towards us. This is not truly clockwise. It's actually counterclockwise. So this would be S. So we have R2-chlorobutane and S2-chlorobutane. And we said that these are enantiomers. They are non-superimposable mirror images of one another. That is the definition of enantiomers. They are non-superimposable mirror images. So I want to go over a couple ways that you can draw enantiomers. Let's start with a chiral molecule. We'll use an easy example. We'll use 2-chlorobutane. So we'll draw our butane, 1, 2, 3, 4 carbons, and we'll give our chlorine a wedged bond. Like that. Now, this is the R. Let's go ahead and prove that it's the R. On our asymmetric carbon, which is carbon number 2, there are 3 groups. Again, or there are 4 groups. Again, there's the carbon, that's the methyl. There's the carbon, that's the ethyl. There's the chlorine, and there's also a hydrogen. I'm going to draw in the hydrogen here, just so we see it. And again, we can assign these groups stereochemical priority. Chlorine would be the highest. Our carbon attached to another carbon would be 2. Our carbon with only hydrogens would be 3. And our hydrogen going back would be 4. If we look at our 3 highest groups with the H going away, we see that it's going clockwise from 1 to 2 to 3. So that is the R. There's our R. Now, to draw the enantiomer, you can do a couple things. Since the definition of an enantiomer is the non-superimposable mirror image of a molecule, we could literally draw the mirror image of this molecule. Let's go ahead and do that. Let's imagine that we've got a mirror like so. Let's reflect everything across the mirror. So we would get something like this. There we go. Every single carbon got mirrored across that plane. We can give our assignments. They should stay the same. The chlorine carbon is 1. The ethyl carbon is 2. The methyl carbon is 3. And now again, you see that by reflecting the molecule in a mirror, the directionality of our groups will change. The mirror image has our groups going in the opposite direction. So now we've got the S. So that's one way to draw the enantiomer, is to literally imagine a mirror and reflect everything in the structure across the mirror. There's perhaps an easier way to do it. If you've got a really complicated molecule with lots of different structural aspects, lots of different stereochemical aspects, it can be pretty tedious to reflect every single thing across a mirror and do it accurately. So an easier way to do that would be to change all the wedges into dashes and all the dashes into wedges, but change nothing else. Leave everything else exactly in place. So I'm going to do that starting with our R version, and I'm going to draw everything exactly the same, except I'm going to change a wedge to a dash. So we'll do this. 1, 2, 3, 4. There's our 4 carbons. Everything in place except where we have a wedge, I'm going to turn it into a dash. There we go. So we can give our priorities. All the groups should maintain the same priority. Chlorine is going to be 1. Ethyl carbon is going to be 2. Methyl carbon is going to be 3. But now, because we changed that wedge into a dash, we basically took the chlorine off and popped it back onto that same carbon, but from the back side. What we also do concomitantly by doing that is we also remove the hydrogen from the back and we pop it onto the front part of that carbon, which means that now, even though from 1 to 2 to 3, it looks like we're going clockwise, the H is now coming towards us. The fourth stereochemical priority group is coming towards us. So our definitions change. So this is by definition the S. All I did was I changed every wedge into a dash. Now, what that means, first of all, there are two ways to draw the stereochemical mirror image of that. The enantiomer is to either literally draw the mirror or to keep everything else in place and change wedges to dashes and dashes to wedges. Let's look at these two things. If both of these things are the S, that means they're the same. If we look at these, hopefully you can see why they're the same. If we take our bottom structure and we flip it over like that, we flip it around, you end up with the ethyl group over here. You end up with the methyl group over there. That's what we have here. We have the methyl group here, the ethyl group there. And the chlorine was back, but we flipped it over. So now we flipped the whole molecule over. So now it's coming forward. That gets us to our original mirror image, meaning that by either drawing the mirror of our first structure or taking our first structure and changing the dash into a wedge or the wedge into a dash, we get the same results. We get the enantiomer. Let's look at the pyrrolidine that we just did. So the one that we named was 2R3R, 2,3-dimethylpyrrolidine. What would happen if we changed the configuration of both of these carbons? Instead of having this methyl be a dash and the hydrogen a wedge, we flip that around and have it be a methyl wedge and the hydrogen dash, and do the same thing for this carbon. Instead of the methyl being a dash, we make the methyl a wedge. Well, if we're changing the configuration of those carbons, instead of being in the R configuration, you would find that they would be in the S configuration. So we have 2R3R, we have 2S3S. And we do that by changing the dashes into wedges and keeping everything else the same. Those are non-superimposable mirror images. All of the R's have turned into S's. So we would call those enantiomers. All the R's have turned into S's. These molecules are non-superimposable mirror images. Now, if we change only one of the configurations of the carbon, so let's say we change the configuration of this carbon, but leave this carbon in the same configuration, we would get this guy, where we have now flipped this methyl into a wedge and left this one as a dash. So the one that we flipped was the 2. That was the 2 carbon. So the 2, instead of being 2R, is now 2S. But 3R remains 3R. Now, those are not enantiomers because they are not non-superimposable mirror images. They're not mirror images anymore. You can't have a dash, for example, appear as a wedge in a mirror. It didn't work. A dash will appear as a dash in the mirror. So these guys are not enantiomers. There's another relationship for that. I'm going to talk about that in a minute. But these guys are enantiomers. If we take this wedged methyl and reconfigure it as a dashed methyl, the S would become an R. And if we take this dashed methyl and reconfigure it into a wedged methyl, that R would become an S. So these guys are non-superimposable mirror images. All of the configurations have changed. We go from a 2s to a 2r, and from a 3r to a 3s. So those are enantiomers. Anytime you have all of the configurations changing, all of the r's become s's, or all of the dashes become wedges, or all of the wedges become dashes. If all of the configurations change, that pair of molecules are called enantiomers. If some of the configurations change, but not all of them, meaning some of them change, some of them stay the same. For example, like these guys here, this pair, the 2 configuration changes from R to S, but the 3 configuration stays the same. Or these guys, where the 2 configuration changes and the 3 configuration stays the same. Or the diagonals, where the 2's stay the same and the 3's change. Or these diagonals. Those are called diastereomers. It's a stereochemical relationship where they are not cis or trans geometry isomers. They are not constitutional isomers. And they are not enantiomers. They are not non-superimposable mirror images. But there is a relationship. It's just not defined in any of those other terms. So we call them diastereomers. So those are diastereomers because some of their configurations change, some of them stay the same. Those are diastereomers, okay? And those are diastereomers, up and down. There's another way to view stereochemical molecules, and that is by a method called a Fischer projection. You will remember from a few lectures ago, we talked about Newman projections. It was a way to view a molecule in such a way that it was easy to perceive their rotational configuration, how one group was positioned in space versus another group, and how you could rotate one group around to align groups or stagger groups with one another. That was the Newman projection. And again, the point of it was to view a molecule in a meaningful way, to get a better picture of the molecule as it applies to a certain problem that we're trying to solve. Fischer projections are yet another method for doing that. It's a way to view a stereocenter in such a way that a lot of information is communicated in a very simple way. So see if you can follow this. By the way, Fischer projections are used a lot in biochemistry. So they might not come up a lot in this course. When we talk about carbohydrates at some point, we will use Fischer projections. But for the most part, we can get by just using line angle structures. But in biochemistry, you will use Fischer projections a lot. So think of this as a prereq for any future classes you take in chemistry. Here's our stereochemical molecule. We've got 4 dissimilar groups: group 1, group 2, group 3, group 4. Here they've assigned these groups. Group 1 is an OH, group 2 is a carboxylic acid, group 3 is a methyl going away, and group 4 is a hydrogen coming towards us. We are going to view this molecule so that we are looking at the carbon from between the largest priority group and the lowest priority group. So between group 1 and group 4. So imagine we're kind of looking at this molecule right up from between groups 1 and 4. If you view this molecule from that angle, it would look like this. This is what you would see. You would see group 1 coming out towards you from the left, or going out towards the left towards you. Group 4 coming outwards toward the right. You'd see group 2 and group 3 going away from you above and below the carbon. Again, looking at the molecule kind of from this perspective, right? This angle right here. You'd see this. Group 1, Group 2, Group 3, and Group 4. Then what we do is we just draw a set of perpendicular lines like this. And it is assumed that we know that that center point where these lines cross is a chiral carbon, a asymmetric carbon. So we would draw it like this. This molecule, drawn this way in a perspective drawing, can be simplified in a certain way to look like this. And again, you're always going to have the highest priority group on the left or the right, and the lowest priority group on the right or the left. You're always going to look at it from between groups 1 and 4. So depending on whether group 4 is here and group 1 is there, or vice versa, you might have groups 1 and 4 on opposite sides, but they will always be on the sides. So when you view a Fisher projection, it is assumed that group 1 and group 4 are coming out at you. That the molecule really looks like this because it really looks like this. So watch what happens when we do stereochemical assignments in a Fisher projection. Again, we can follow this through. Remember, the carbon, the highest priority group on that central carbon is the oxygen. So the OH is highest priority. Then we have 2 carbons. This is a carbon with 3 hydrogens. This is a carbon with 2 oxygens. So the carbon with 2 oxygens gets higher priority. Then the methyl is the 3rd, and hydrogen is, of course, the 4th. So if we look at these first 3 groups, group 1, group 2, group 3, you'll notice that they're going clockwise. That's fine. But this is S. Why is it S if we're going clockwise? Well, why would it ever be S if we're going clockwise? The only time that you would have an S configuration when you're going clockwise is because the smallest group, group 4, is coming out at you. Again, we are looking at this molecule from the perspective of the smallest group coming out at us. So in a Fisher projection, you will always have the smallest group on this horizontal line. By definition, one of these 2 groups on the horizontal line will always be group 1 or group 4. So be very careful with that, because the 4th group will always be on the horizontal line and therefore will always be oriented towards you, means that your stereochemical definitions, clockwise versus counterclockwise, mean the opposite of what we're used to. In a Fisher projection, clockwise will be S and counterclockwise will be R. Again, that group is coming towards us. We can practice real quick. Let's look at this stereochemical carbon, this assignment. Notice, by the way, that this is a Fisher projection with 2 chiral centers. We have the carbon here, that's at the crisscross, and the carbon here, that's at the crisscross. So let's look at the 4 groups that are attached to this carbon. We have an oxygen, we have a carbon, we have another carbon, and we have a hydrogen. So between those 4, O is the highest, H is the lowest. Then we have a carbon with 2 H's and an O, or a carbon with an H and an O and another carbon. So this carbon down here will get higher priority than this carbon up here. So this top assignment would look like this: 1, 2, 3, and our hydrogen is 4. So we are going counterclockwise from 1 to 2 to 3. We're going counterclockwise. But because this is a Fisher projection, we know that this H is coming towards us. So this should be R, not S. We'll do the same thing down here. Let's clear this. let's assign this carbon's stereochemical priority. We have an O, we have an H, we have a carbon, and we have a carbon. So the O would have the highest priority, the H would have the lowest priority. Again, those are going to be the groups on the horizontal. Those should always be your highest and your lowest on one side or the other. Then we have to break the tie between the two carbons. This carbon has an O, an H, and a C. This carbon has two H's and an O. So this carbon would get higher priority than this carbon. So we would go 1 on the O, 2 to 3. Again, we are going counterclockwise from 1 to 2 to 3, but the H is coming towards us. Remember, it's always going to be backwards in a Fisher projection. So counterclockwise is R. So we have that guy is R and that guy is R. Be careful. Notice that it doesn't matter that these OHs are on the opposite sides. It doesn't matter that these H's are on opposite sides. It turns out being that each one of these carbons is R anyway. So please don't try to take silly shortcuts. Don't try to make assumptions that just because something is a wedge, it's going to be S. Or just because something is a wedge, it's going to be dash. Or just because an OH is on the left, it's going to be an R. Or something's on the OH is on the right, it's going to be an R. Do not make silly assumptions like that. You always will need to check your priority and figure out whether it's going counterclockwise and figure out whether your H is going in the right direction or not. Okay, a couple more things to cover. There is a special class of molecules called mesocompounds. Mesocompounds are molecules that have asymmetric carbons but are not chiral. That's very weird. Remember, we said that in order to have chirality, you need an asymmetric carbon. You need at least one asymmetric carbon. Then I told you there are some exceptions that I'm going to show you in a work group that are molecules that have no asymmetric carbons but are still chiral. There's kind of a weird trick to them. Mesocompounds are the opposite. These are molecules that are achiral. They are not chiral, even though they have asymmetric carbons. This is a perfect example. You'll notice that this molecule has two asymmetric carbons. These starred carbons, this guy has a methyl carbon, a ring carbon with two H's and the rest of the ring, a ring carbon with one H, a methyl and the rest of the ring, and a hydrogen. So this carbon has 4 dissimilar groups. So that is a chiral center. This carbon also has 4 dissimilar groups. We have a methyl. We have, again, a ring carbon with a methyl, an H, and the rest of the ring, and a ring carbon with 2 H's and the rest of the ring. So, and then the hydrogen. So 4 different groups, 4 dissimilar groups on this carbon. We could assign priorities. We would give this guy highest priority, this guy second priority, methyl the third priority. The hydrogen is coming towards us. So 1 to 2 to 3 is clockwise, but the H is coming towards us, so it's S. We could give this guy priority or priorities. Carbon 1, highest priority over here. The other ring carbon is priority 2. The methyl is priority 3. They are going counterclockwise, so normally it would be S, but the fourth group, that H, is coming towards us, so it's R. So we have a molecule with 2 different stereocenter carbons. One of them is in the S configuration, the other is in the R configuration, but notice that our molecule, it has an internal plane of symmetry. Remember we said that when a molecule or an object has an internal plane of symmetry, when you reflect it in a mirror, the object in the mirror will be the same as the original object. And so it's not chiral. It does not have a left-handed form and a right-handed form. Its mirror image will be superimposable. Here's another example. Here's a ring. This is kind of what we just looked at. We had a 5-membered ring with 2 groups going away from us and 2 hydrogens coming towards us. Here we have a 5-membered ring with 2 hydrogens coming towards us, 2 chlorines going away from us. We have this internal mirror plane. If you reflect this in a mirror, I think we did that back here somewhere, this picture here. Since we have this internal mirror plane, when we reflect that object in a mirror, we get the same object. We don't get a different object. This is a chiral this is an achiral molecule. This is actually a meso compound. A meso compound is one where we have stereochemical asymmetrical carbons, but overall we have an internal mirror plane. That prevents us from getting stereochemistry. Same thing here. We could have a 6-membered ring where we have 2 bromines going down and 2 hydrogens going up, for example. We have an internal mirror plane. That is a meso compound. It's achiral. In a Fisher projection, you can very clearly see these internal mirror planes. This molecule is reflected, the top part is reflected on the bottom part. Here, the top part is reflected on the bottom part. We'll talk about tartaric acid at some other point in this class. It's a very interesting molecule. Actually played a very central role in the discovery of chirality in the first place. Since we've learned about free radical chain reactions, I want to talk about the products of halogenated alkanes. Here's an example of a free radical halogenation. We would take, say, butane and brominate it, Br2 and light. And since we have primary carbons and secondary carbons, we know that we would end up with a radical on the secondary carbon, and therefore we'd have a bromine on the secondary carbon. We've always drawn the line as our product. What that means, though, be aware of this. When a line is drawn, not dashed or wedged, it means that you make both the dashed product and the wedged product. That both of these are present. It means that we are not specifying one or the other, but rather we are specifying that both can be formed. When you have an equal mixture of enantiomers, so if you go through and count this, this would be the R enantiomer, this would be the S enantiomer. If you have a 50-50 mixture of both, where one can be formed just as easily as the other one could be, we call that a racemic mixture. Imagine that you've got that radical. Let's say that we generate our radical from the Br2, we split that with light. The bromine radical removes a hydrogen from the secondary carbon that makes HBr and leaves us with our secondary radical. That is a planar structure. And we can add the bromine from the top and get the bromine up, or we can add the bromine from the bottom and get the bromine down. Since the radical is a planar structure, there's no preference for adding the bromine to the top plane, top of the plane, the top face, or the bottom face. And so if you add it from the top face, you might get the wedge like this. You add it from the bottom face, you might get the dash like this. So when we do free radical halogenation, we will often be generating chiral molecules. We will be introducing stereochemistry into our product. Since we can't control that, we should assume that we get 50-50. We get half of the wedges, half of the dashes. So it would be fair to just draw the line, because that line means that we are not specifying that in fact we mean both, not one or the other, but both. There sometimes can be directionality that is influenced in this. For example, now I'm going to cheat a little bit. Here's a chiral molecule. We've got a carbon here with a methyl, an ethyl, a T-butyl group, and a hydrogen. So we have a chiral carbon. This molecule is chiral. In fact, I think this is R. You can check it. I think that's R. Let's imagine, like I said, I'm going to cheat a little bit. Let's imagine that we put a bromine on here by way of free radical halogenation, and we're going to put it on the secondary carbon. Yes, it's true. You're right that if we were to do a free radical halogenation, it would go on the tertiary carbon right here. But just for the sake of argument, let's put the bromine on the secondary carbon, because I want to show you how the T-butyl group can influence the chemistry of other reactions that are going on. Here's the radical that would lead to our product. We would remove, say, a secondary hydrogen, make a secondary radical. Because the bromine is up, because the T-butyl group is up, it's going to block the top face of the molecule. The bromine, Br2, is not going to be able to access the radical from the same face as the T-butyl group. That T-butyl group is a big, bulky group, and it's going to block the top face since it's on the top. So the attack from the bottom, bromine approaching that radical from the bottom, is going to be much more likely to happen. It's going to be more accessible from the bottom. So since we can put bromine on the top or on the bottom, but it's going to be more likely to add from the bottom than the top because the T-butyl group is blocking it, we are going to have one product that's formed in preference to the other. Now again, I just want to reiterate this. The real major product would have the bromine on the tertiary position. But amongst the secondary positions, the bromine going away from the T-butyl group will be in preference to the bromine going in the same direction as the T-butyl group. These are diastereomers. Notice that between these two products, the stereochemistry of the T-butyl group is the same. It does not change, but the stereochemistry of the bromine group does. So, like we said, if all of the groups change configuration, they are enantiomers. But if only some of the groups change and some of them stay the same, they are diastereomers. This is what we call diastereomeric excess. That's a very important aspect of stereochemistry, in that bulky groups can direct the reaction to take place from one face, or in this case the bottom face, rather than the top face. So pay attention to that if you ever deal with big bulky groups that are oriented on one side of the molecule but not the other. It's likely to direct any reactions in a certain direction. Chirality plays a very important role in biology. Most biological molecules are in fact chiral. And most biological processes are very specific as to only react with one handed form of the molecule. For example, a protein might only bind to the R enantiomer of a drug and not the S enantiomer of the drug. Or it might be the case that one enantiomer has a certain effect on the body and another enantiomer has no effect, or a much greater effect, or a completely different effect. We've already mentioned that a 50-50 mixture where both enantiomers are present in equal proportion is called a racemic mixture, or that mixture is called a racemate. If you have only one enantiomer present, for example, if all of your molecules have their stereocenter in the R configuration, or all of your molecules have two stereocenters and they're both in the S configuration, or all of them are RS or all of them are SR, we call that enantiomerically pure. So an enantiomerically pure substance has only one enantiomer present, the other one is not present. A racemic mixture or a racemate has both enantiomers present in equal amounts. So many drugs on the market are racemic mixtures. There's a drug called ketamine, which is an anesthetic. Its use is really limited because it has a stereocenter, and one form of the molecule has one effect on the body, and the other form of the molecule has a completely different effect. Like it says here, the S isomer is responsible for the anesthetic effects. The R isomer causes hallucinogen, is a hallucinogen, causes hallucinations. So if you want to dose somebody with ketamine, you either have to give them a racemic mixture of R and S, in which case they will get both effects. They will get the anesthetic and the hallucinogen, or you have to go through great extent to separate the S enantiomer from the R enantiomer. And as I'm going to show you in a couple slides, it's very difficult to separate one enantiomer from its twin. Here's an example. Here's R2-bromobutane and S2-bromobutane. They have the same boiling point, so you can't separate them by distillation. They have the same melting point, so you can't separate them by recrystallization. They have the exact same refractive index, so you can't identify them by looking at how they bend light through their solution. They also have the same density, so you can't separate them by separatory effects, by a separatory funnel. There is one way that we can tell enantiomers apart, and don't confuse this with refractive index. Refractive index says, to what degree do they bend light as light goes through their solution? What light does, however, is it will get rotated, not bent, but rotated. This is thyroid hormone. Thyroid hormone is a chiral molecule. It's got an asymmetric carbon right here. This carbon's got an H, an NH2, a carboxylate group, and this big piece over here. 4 different groups. It is present in the S form and the R form. And what chiral molecules do is they rotate polarized light. Polarized light is light that has all of the, say, waves vibrating in the same plane or the same direction. If you take a light bulb emits light in all different directions so that its waves are oriented in all different positions relative to some axis. If you pass that light through what's called a polarizing filter that has these little tiny slits going all the same direction, only the waves of light that are aligned with those slits will make it through the filter, and you'll end up with plain polarized light. That is light that has all of its waves vibrating in the same plane. If you take light and you polarize it and you let it pass through a sample of a chiral molecule, it will rotate light in a certain direction. You see here the light is all vertical, and as it passes through our sample of chiral substance, the light gets rotated in a certain way by some degree. So chiral molecules rotate polarized light. Two enantiomers, any two enantiomers, that is to say molecules that have the same connectivity but the different orientation around an asymmetric carbon, or 2 or 3 or 4, will have identical physical properties except for the direction that they rotate the plane of polarized light. Enantiomeric compounds will rotate light in the exact same degree and the exact same amount, but in opposite directions. So, for example, if an R enantiomer rotates the plane 30 degrees clockwise, the S enantiomer will rotate it 30 degrees counterclockwise. If the R enantiomer rotates the plane counterclockwise, S will rotate it clockwise. They do the same degree of rotation, but in the opposite direction. Now, you can't predict what direction a particular enantiomer will rotate light for any given molecule. These things are empirical. They have to be determined through experiment. But whatever direction a molecule happens to rotate, the R enantiomer does. The S enantiomer will do the opposite. R and S are simply names that we give to a structure. We can look at a structure, we can say whether it's R or S, but the direction that they will rotate light and the magnitude of that direction are physical properties that have to be measured. Now, this is what we call specific rotation. The degree and magnitude, the direction and magnitude of that rotated light is called the specific rotation of a molecule. And this is a characteristic physical property, meaning that it is a way that we can tell the identity of a molecule. Furthermore, we can use it to determine what proportion two enantiomers are present relative to one another. For example, let me show you how this works. We can have, let's say, 2-butanol. It's a chiral alcohol. It has an S form and an R form. So these are enantiomers. And it turns out that the S form of 2-butanol rotates light positive 13.5 degrees, and the R form of 2-butanol rotates light negative 13.5 degrees. If you have a racemic mixture, that is to say, a 50-50 mixture of S2-butanol and R2-butanol, there will be no net optical rotation. Basically, every time light gets rotated 13.5 degrees by the S molecule, an R molecule will rotate at negative 13.5 degrees. So there will be no net optical rotation because it is a 50-50 mixture. Look at this. If we have 75% S and 25% R, so this is not racemic, we say we would have 50% excess. We have 50% excess S, 75 to 25. That will have an optical rotation 50% of the specific rotation of S. We are 50% excess in S, so we will be 50% of the way to the optical rotation. If we have zero excess, 50-50, there's no rotation. 50% excess in S will be 50% of the way, 6.75 degrees is 50% of the way to the S rotation. If we have, let's say, 90% R and 10% S, that's 80% excess in R. So our optical rotation of that mixture will be 80%, 10.8 degrees, 80% of the rotation of the pure R. So we can use optical rotation as a way of measuring the proportion of one enantiomer relative to another in a mixture. 50-50 will have 0. And as we move towards 100% excess, we will have our rotation move towards that optical rotation, that specific rotation, based on the percent excess. Here's kind of a cool story about chirality. Remember, I mentioned that different enantiomers can have different effects in biological systems. This is a molecule called thalidomide. It is a drug that was prescribed in the late 60s, if I recall, as an antiemetic. That means it's an anti-nausea medicine. And it was prescribed to pregnant women to treat morning sickness. And it was very, very widely prescribed because it was very, very, very effective. But there was something that was a bit hidden in thalidomide that doctors and scientists didn't fully understand at the time. And that was that there is a chiral center. This carbon right here is chiral. It has a nitrogen. It has a carbon with a double bonded O. It has a carbon with 2 hydrogens and the rest of the ring. And it has a hydrogen that's not drawn. So after a couple years of thalidomide being prescribed pretty widely for morning sickness to pregnant women, there was a huge spike in birth defects. And they were pretty severe birth defects where babies were being born with severely deformed arms and legs, hands and feet. Sometimes they were missing arms and legs or hands and feet altogether. Very, very severe birth defects. And it was found that because there are 2 enantiomers of thalidomide, and thalidomide was being dosed as a racemate in a racemic mixture, both the R form and the S form were being dosed. The S form was what was causing limb deformities. The R form, it turned out, was the effective sedative drug. So you were getting both the effects of both enantiomers because they were being dosed in a 50-50 mixture. So there was the obvious solution then, of course, was to separate, remember to go through great lengths to separate the S form from the R form. So when they did that and they dosed only the R form, you still got limb deformities. And that was very puzzling. But what it turned out, and we will cover this in second semester, in our second 6 weeks of this course, that there is a specific type of reactivity at this carbon. And what was happening was that in the acidic conditions of the patient's stomach, when it was dosed and you take the pill and the pill goes into your stomach, under acidic conditions, this carbon can undergo a reaction that will cause the R form to become the S form. In fact, it allows it to convert back and forth. So it turned out that even if you dosed pure R in the body, the R would convert to the S would convert back to the R, back and forth and back and forth and back and forth, until eventually you had 50% S, 50% R in your system, and you still ended up with birth defects, limb deformities. So thalidomide had to be taken off the market because there was no way to avoid dosing the enantiomer that had these negative effects. Here is a logical decision tree to explain the relationships of different isomers. We're going to start by looking at any 2 structures. From those 2 structures, we need to decide, are they the different formulas or are they the same formulas? If they are different formulas, then they're clearly different molecules. So we're not talking about isomers. But if they are the same formula, we have two different questions. Are they different species or are they identical molecules? If they are identical molecules, then we might be talking about conformations. Remember, we talked about conformations of butane or conformations of propane or conformations of cyclohexane, a chair. When we change butane from trans-butane to cis-butane by rotating around that single bond and having our dihedral angle go 0 to 180, it's all butane. It's just changing conformations. So the same thing would be for chairs. If we have a group axial and we flip the chair and we make that group equatorial, we are changing the conformation of the chair. We are not changing the molecule. It's the same thing. So those would be conformations. But if we have different molecules, different species, then they are isomers. Same formula, different molecule are isomers. If the connectivity is different, then they are constitutional isomers. If the molecules are literally connected in different ways, different atoms are connected to each other, then you have constitutional isomers. If they have the same connectivity, then those molecules are stereoisomers. Those stereoisomers can either be geometric, meaning they are EZ, entgegen zusammen, meaning they have different geometry around a double bond, or they are what we call configurational stereoisomers, meaning that they differ because of an asymmetrical carbon. If the two molecules are configurational, they are different because of an asymmetrical carbon, and they are non-superimposable mirror images, then they are enantiomers. If they are not enantiomers, meaning if they are configurational, but they are not non-superimposable mirror images, then they are diastereomers. You can see here I drew enantiomers where all the dashes turn into wedges and all the wedges turn into dashes. The diastereomeric pair, we have one configurational carbon that stays with the wedge, and the other carbon changes from a wedge to a dash. So remember, for enantiomers, all the dashes and wedges need to change. For diastereomers, only some of them do. One other note is that geometric isomers are technically diastereomers. I don't have them related in this tree, but technically you can think of geometric isomers as being diastereomers because they have one carbon whose stereochemistry changes, and one carbon whose stereochemistry stays the same. If you change one carbon in a double bond, but not the other, you end up with geometric isomers. That is kind of what you're doing with diastereomers, only you're doing it with a asymmetric carbon, a tetrahedral carbon with 4 dissimilar groups, rather than doing it with a double bonded carbon with only 3 dissimilar groups. Here's what I mean by that. I say geometric isomers are technically diastereomers. Here I've got diastereomers, where I've got a pair of molecules where one asymmetric carbon stays the same, the carbon with the bromine in this case, and the other asymmetric carbon changes, the carbon with the chlorine in this case. 2 stereocenters, one is identical between the 2 pairs, one is inverted between the 2 pairs. If we look at geometric isomers, we have kind of the same thing going on, where the carbon on the left has the fluorine on top and the chlorine on the bottom in both cases. But the other carbon, the carbon with the bromine and the iodine, that changes between the 2 pairs. So you can think of it as kind of having 2 stereocenters where one of them is identical between the two pairs and the other one is inverted between the two pairs. The only difference again is that in the top case, they are tetrahedral. In the bottom case, they are planar. What's the difference? The difference is that if you invert both of the stereocenters, you end up with the same molecule when you have geometric isomers. So if you have a double bonded carbon and you change the groups on both of the carbons, so we change the fluorine and the chlorine, and we change the bromine and the iodine, you end up getting the same molecule back. On the other hand, if we have tetrahedral configurations and we change both of the groups, you end up getting enantiomers, not diastereomers. You don't get the same molecule back. So they're technically the same, but they're a little bit different. I would prefer that you stay with the original picture that geometric isomers are geometric isomers and diastereomers are diastereomers. Don't stress too much about geometric isomers also being diastereomers. Just in case you ever come across that, if you're reading up on a website or some other textbook, or you hear from some other professor refer to these cis-trans or EZ stereoisomers as being diastereomers, that's technically correct. It's just a little bit easier to keep it organized in your head if you do it this way. Recall from lecture that when we had one stereocenter, that stereocenter could be R or it could be S, meaning one stereocenter gave rise to two possible stereoisomers. Additionally, we looked at a situation where we had two stereocenters and we ended up with four stereoisomers. We had, for example, an RS, the enantiomer, the SR, then a diastereomer of that would be RR, and the enantiomer of that would be SS. We have four different ways that those two stereocenters could be configured. So two stereocenters gave rise to four possible stereoisomers. If there were three, let's think about what those combinations could be. We could have RRR and SSS. Those would be enantiomers. We could have RRS and SSR. Those would be enantiomers. We could have RSR and SRS. Those would be enantiomers. And SRR and RSS. Those would be enantiomers. So you have 8 possible configurations coming out of 3 stereocenters. All of the other relationships, so for example, RRR to RSS or RRS to SSS or to SRR, all of those other combinations that are not related as enantiomers are diastereomeric relationships. So the equation, the pattern, is that the number of stereoisomers X will be 2 to the n, where n is the number of stereocenters that you have. You'll see that meso compounds violate this. So normally we would say that if we have 2 stereocenters, you should get 4 possible stereoisomers. But let's look at what happens when we use meso compounds. Let's start with RS. And let's draw the enantiomer of the RS. So we're going to draw everything in the same position, but we're going to change all of our wedges into dashes and all of our dashes into wedges. So the RS would turn into the SR. But remember, because this is a meso compound, its mirror image, which is what you get by changing wedges to dashes, is really the same thing. So we do not have enantiomers. It's not chiral if it's a meso compound, but we can have diastereomers. The RS is a diastereomer of the SS. And the RR is also a diastereomer of the RS. So those are diastereomers And those diastereomers are enantiomers of each other. The SR is chiral. It's no longer got that internal mirror plane. And the RR is chiral. It no longer has that mirror plane. So we have the RS, which is meso. It does not have any evil twin. It does not have an enantiomer. It's all by itself because it's achiral. Then we also have the SR, then we also have the SS and the RR. So we have 3 instead of 4. With meso compounds, the one symmetrical molecule does not have a twin. Only the asymmetrical ones do. So you kind of end up with 2 to the n minus any number of meso compounds, one meso compound. So you end up with 3 instead of 4. So the 1,2-dimethylcyclopentane has 2 stereocenters, but only 3 stereoisomers. The SS, the RR, and the meso, which is RS or SR being the same thing. Here are a couple examples of molecules that are chiral, but do not have any stereocenters. They don't have any asymmetrical carbons that have 4 dissimilar groups. The first one is kind of a cool example. These are 2 benzene rings that are connected, and the benzene rings have a couple groups coming off of them. In this case, I used a fluorine and a methyl and a bromine and a chlorine just so we could differentiate them. But because of the way that these groups are pointing towards one another, they will cause the rings to kind of pop out of plane with each other so that they sit perpendicularly. That way the groups, the chlorine, fluorine, bromine, and methyl, are displaced far away from one another, such that you end up with this kind of perpendicular arrangement of the groups. Imagine that we're looking down this dotted line, the point of view of the end of this molecule. We would see a fluorine and a methyl up and down, and a bromine to our left and a chlorine to our right. But depending on how that molecule is arranged, depending on what direction those rings point relative to one another, you would get a different arrangement. You would get a clockwise arrangement and a counterclockwise arrangement. And as long as these groups are bulky enough, the rings will be locked in that configuration. They won't be able to rotate so that those groups can pass by one another. They will just kind of lock into that one position, and you end up getting a molecule that rotates polarized light just like any other chiral molecule. It's got a defined arrangement of these atoms in space that you can't interconvert just by rotating bonds around. The point is that these bonds don't rotate anymore because the rings are locked in that configuration by these bulky groups that are repelling each other. So that's pretty cool. Another one is this guy, where we have this carbon with the methyl and the hydrogen, and you see that methyl and the hydrogen are drawn as wedges and dashes, and so it kind of looks like a stereocenter. But if you follow the ring around, you end up with that carbon only having 3 groups. There's the methyl group, the hydrogen, and then the 2 ring carbons are the same, and you can follow that ring around, and at no point will you be able to differentiate one of those carbons from the other. That carbon technically does not have 4 dissimilar groups attached to it, but they are non-superimposable mirror images because of the way that the chlorine comes off the double bond. You'll notice that these molecules that I drew are drawn as mirror images of one another, but they are not superimposable. You can't just take the molecule on the right and slide it over and have it line up with the molecule on the left, nor can you flip it over because then your methyl groups and your hydrogens will be pointing in the wrong direction. So here, in this case, we have non-superimposable mirror images, even though we didn't have any asymmetric carbons. So again, these are some exceptions, but by and large, you do need an asymmetric carbon in order to get chirality. That's the end of lecture 7. That's chapter 5 in Wade. The workshop, Stromanus chapter 12, covers all aspects of stereochemistry and a few other interesting little tidbits that you should practice and read over so that you understand this before we move on to new material.